Okay, let's pick up where we left off on Wednesday. We are looking at chemical reactions, and we were talking about catalysts. A catalyst will increase the rate of a chemical reaction. Now, we mentioned that chemical reactions are affected by temperature and concentration and particle size. We know that chemical reactions go faster at higher temperatures. We know that the more reactants you have, the faster it will go. This is one of those rare cases where if some is good, more is better. And we know also that the smaller the particle size, the faster the rate's going to go, because it means a small particle size gives you more chances for the reactants to come together. I said the other day, the problem we have in humans is that we're stuck at 98.6 or 37 degrees Celsius. We can't do anything about temperature. We can't raise our temperature to have a more efficient chemical reaction. We are dealing with very, very small concentrations, and so we can't increase the concentration. So we can't affect the rate of the reaction by adding more reactants. And we're already dealing with very, very, very tiny particles. So there's nothing we can do to increase the rate of a chemical reaction in our bodies. So we use a catalyst. A catalyst allows the reaction to go faster. And the catalyst that we use is what is known as an enzyme. It's a protein that can change the rate of reaction. We can't do anything about particle size or temperature or concentration, but we can make lots of enzymes. And enzymes simply work by grabbing two reactants and bringing them together. So normally in a chemical reaction, we would wait for the two reactants to bounce into each other. That's why particle size is important, where we have lots and lots of particles, they can bounce into each other. Where we have more, the concentration is greater, they can bounce into each other. And if the temperature goes up, they're going to move faster and bounce into each other. Well, we're sort of, to make the reaction, the only thing we can do in our bodies is produce enzymes that will simply flood an area and grab the reactants and bring them together. And that's what they do. They make a chemical reaction go faster without themselves being used up in the reaction. They don't become part of the reaction. They bring the reactants together, the reaction occurs, and they let it go. They go out and do it again and again and again. So this is how we get chemical reactions to go very fast in our bodies. Since we can't change any of the other parameters, we simply increase the number of catalysts. A catalyst makes a reaction go faster. It's like trying to light charcoal, for example. The catalyst is the lighter fluid. If you stand there with a pile of charcoal and toss a match on it, you're going to be doing that all day. You're not going to get the charcoal to burn very, very easily. I mean, you could, but it would be a very tedious process. You soak the charcoal with lighter fluid and you ignite that, and that gets the charcoal burning. It makes the whole reaction go faster. So, okay, moving on now. We've looked at inorganic materials, or we looked at some. We looked at water. Now we want to take a look at biochemistry, the chemical reactions that take place inside the human body. Chemistry alone is mixtures and solutions and compounds and covalent bonding and ionic bonding and stuff like that. But this type of situations. How does that apply to us? And that is where we get into biochemistry. The chemicals in our bodies are either going to be considered inorganic or organic. The inorganic compounds are the waters, the salts, the acids, and the bases. Plasma is water with sodium chloride in it. We generate carbonic acid when we release carbon dioxide. We use bicarbonate to neutralize that. We are always dealing with sodium chloride in our bodies. That's one of the many salts. The big key about what we consider to be an inorganic compound is, does it contain carbon? Carbon is the key. Inorganic compounds don't contain carbon. The one exception is carbon dioxide, CO2. That is an inorganic compound, but it does contain carbon. And also we would throw in there carbon monoxide, CO. CO2 is carbon dioxide, CO is carbon monoxide, one oxygen. If that's what you get when you as they say, the product of incomplete combustion, you worry about carbon monoxide being released when you're burning fuel. Okay, the organic compounds, the much more interesting compounds, are the carbohydrates, the fats, the proteins, and the nucleic acids, the DNAs, for example. They all contain carbon. They're all large molecules. They're all covalently bonded. The inorganic compounds may or may not be covalently bonded. They may be ionic bonds. They may be hydrogen bonds. They may be small molecules. They usually don't contain carbon. So the difference is organic compounds have lots of carbon. They have either the sugars, the fats, the proteins, and the nucleic acids. They're all covalently bonded. They all have a great deal of potential energy. All the organic compounds have a great deal of potential energy. Methane, natural gas, the stuff that we burn for fuel, has a great deal of potential energy so that we can use it as a fuel. We can release that energy when we burn it. Our bodies, however, we're not worried about burning methane. Right now, our bodies are concerned about the inorganic compounds and the organic compounds because we have to have both. So, the number one inorganic compound is water. It represents about 80% of our body's volume. While a water molecule is held together with covalent bonds, there is no carbon involved here. And water has some very unique properties. We have its high heat capacity, its high vaporization heat, it's a polar solvent, its reactivity, and its cushioning properties. So what does all that mean? Well, it takes a lot of heat to cause even a minor rise in temperature. It takes a great loss of heat to see a drop in temperature. Consider when you take water and put it in a pan on the stove, and you turn on the top of the stove, and it seems to take forever to get the water to boil. To get the water to boil, you have to move those water molecules around faster and faster, so it breaks those hydrogen bonds that hold the molecules to each other, where you finally get that rolling boil, as they say. It takes a lot of heat to get it to do that. It also takes water has to lose a lot of heat before its temperature drops. If you take a tray of water and stick it in the freezer, it will take a long time for that tray to freeze. It takes a lot. Water has to lose a lot of heat before we see a temperature change either way. It's a very stable structure. So in that sense, we don't see us gaining or losing heat in our bodies very easily because of water's ability to absorb heat or release heat. Water allows us to cool down though. It will take a lot of heat energy and use that to vaporize, and that's how we cool down when we sweat, by water absorbing all that heat energy when we get hot. We can the water will evaporate when it absorbs that energy, and removing that heat from the surface of our skin cools us down. Water is a polar solvent. It dissolves salts. The positive and negative ends of the salt molecule are attracted to the positive and negative ends of the water molecule. Salt goes into solution immediately. We've all seen that. You add salt to water and the salt dissolves because the salt crystals are being pulled apart right away by the water molecules. If you add sugar to water, it takes a while to get that sugar to go into solution because sugar is not polar. And it takes a lot more energy to get that sugar going into solution. I mean, consider making iced tea, sweet tea. You don't add sugar to cold water. You add sugar to hot water because at least the hot water molecules are moving around faster and it'll break apart the sugar. But if you dump sugar in the cold water, you're going to have sludge at the bottom of your glass or the bottom of your pitcher. And of course, we also use water as our transport medium in our body. Plasma is salt water. Plasma is 90% water. So now what about the salts? You know, we're dealing with salts and water. We have salts are ions and excuse me. Salts are ionic compounds. When they go into water, they will dissociate into anions and cations. Cations have the positive charge. Anions have the negative charge. We call them electrolytes. These electrolytes carry an electrical current, and we use sodium and potassium. We use calcium. We use magnesium as various ions in our bodies. Calcium carbonate, potassium chloride. All of these are important to us in our bodies. Electrolytes help to determine the water concentration in our bodies. Here's what happens to an electrolyte when it hits water. It goes into solution. We see what's happening here. This is sodium chloride, a very common salt in our bodies. When it is exposed to water molecules, the hydrogen end of the water molecule, which has a positive charge, will grab onto the negative chlorine and pull it away from the sodium. The attraction from the positive hydrogen to the negative chlorine is stronger than the ionic bond. And so we pull the water molecule apart. I mean, we pull the salt crystal apart with the water molecule very easily. Another inorganic compound are acids and bases. Acids are known as proton donors. They give up hydrogen ions. The more hydrogen ion an acid gives up, the stronger the acid is. So, and we use two very important acids in our bodies are hydrochloric acid and carbonic acid. Hydrochloric acid is what we use in our stomach to start breaking down proteins, and carbonic acid is what forms when we combine carbon dioxide and water, and it is the primary way one of the ways we move carbon dioxide from the cells to the lungs to get rid of it. We also have acetic acid available to us. Acetic acid is a buffer that will help to neutralize a base. A base is a proton acceptor. Bases grab hydrogen ions whenever they can. Sodium hydroxide, for example, will dissociate into sodium and hydroxide. Sodium has the positive charge and hydroxide has the negative charge. And when we dissolve a base into water, we will also have lots of hydrogen hydroxyl ions. The bases that our bodies deal with are bicarbonate, that's in sodium bicarbonate, baking soda solution essentially, and ammonia. the breakdown of proteins always releases ammonia. Now we measure acids and bases in our bodies and in anything in chemistry using what's known as the pH scale. The pH scale is a measure of the concentration of hydrogen ions in solution. And as I said, the more hydrogen ions you have, the more acidic the solution is. So it's nice to know what our pH range is in our bodies and in things we're dealing with. The pH scale, it's a very simple scale. It is the negative logarithm of hydrogen ions in moles per liter, ranging from 0 to 14. Okay, so it's not such a simple scale, but it really is the way we use it. It's very simple. You know, nobody's going to pay attention to negative logarithms of hydrogen ions in moles per liter. On the other hand, we use the scale from 0 to 14. The negative logarithm, what does that mean? It means a negative logarithm tells you that if you have something that is a pH of 6, it's 10 times more acidic than pH of 7. So you got to remember about the negative log scale. It is something that is a pH of 6 has 10 times more hydrogen ions than something that's pH of 7. Something that is pH of 5 has 10 times more hydrogen ions than something that's a pH of 6, but 100 times more hydrogen ions than a pH of 7. For every change downward on the pH scale below 7, for every number we drop, going from 6 to 5, there's a 10-fold increase in hydrogen ions. So we go from 6 to 5, there's 10 times more hydrogen ions in 5. We go from 5 to 4, there's 10 times more hydrogen ions in 4 than there were in 5. So 4 has 10 times more hydrogen ions than 5, 100 times more hydrogen ions than 6, and 1,000 times more hydrogen ions than 7. And since the more hydrogen ions you have, the more acidic you are, as you go down the scale, you get more and more acidic. To at the very bottom of the scale at 0, you have hydrochloric acid. You know, the hydrogen ion disassociates. We have hydrogen and chlorine, and we have a lot of hydrogen ions. So we go from 7. 7 is the midpoint. 7 is considered neutral. So we go from 7 down to 0 is the acidic side. As our number decreases, the substance becomes more and more acidic. So we go from 7 to 1 or 7 to 0. At 0, we have many, many hydrogen ions. It's a very strong acid. Something that's a pH of 6 is not very strong. It's not a strong acid. It's still acidic, but it's not very strong. Urine can be slightly acidic at pH of 6. You know, and urine's not going to hurt anybody's skin. But hydrochloric acid at pH of 0 can cause some significant damage. If we go up the scale, we see another 10-fold increase. If we go from 7 to 8, instead of hydrogen ions, we have hydroxyl OH ions. So a pH of 8 has 10 times more hydroxyl ions than 7. A pH of 9 has 10 times more hydroxyl ions than 8, and 100 times more than 7. And as we go up the scale towards 14, we get more and more hydroxyl ions. We reach the point where something that's pH of 14, because the scale goes from 0 to 14, something that is 0 to 14 is considered very, very basic. Anything above pH of 7 is considered alkaline or basic. Anything below 7 is considered acidic. As we move up the scale, 8, 9, 10, 11, 12, 13, 14, something that's pH of 14, like sodium hydroxide, has many hydroxyl ions, it is very, very basic. It will cause, something that's a pH of 14 will cause tissue damage. I remember when I was an undergraduate, to demonstrate just how effective sodium hydroxide was at causing tissue damage, they had these pellets of pure sodium hydroxide, and they let us hold one in our hand, and it wouldn't burn or anything, but all we noticed that it was getting slippery, or that the pellet was getting slippery. It was dissolving the fats in our skin. And so we had let go of it and wash our hands. It didn't cause any permanent damage, but it was working so rapidly that it was dissolving the fats, and it was getting, our skin was getting very slippery right around the presence of the pellet. So anything in our bodies, anything below 7 is considered acidic. Anything above 7 is considered basic. 7 is neutral. Now, human blood is slightly alkaline. Human blood runs around 7.4. We are slightly alkaline, probably because of all the carbon dioxide that we're generating from our cells and converting that to carbonic acid. We are not, distilled water is neutral at 7.0. Our blood is not. Our blood is at 7.4. And our blood is very, very sensitive to changes in pH. If our blood is normally at 7.4, we have a very narrow range we can operate in. If we get above 7.45, we start getting in trouble. If we go below 7.35 and become slightly acidic, we start getting into trouble. We like to stay somewhere between 7.35 and 7.45. Anything outside those parameters, we start having problems. And here you can see examples of the various substances that we might encounter on the pH scale, with sodium hydroxide at the very top with a pH of 14, and hydrochloric acid at the very bottom with a pH of 0. Oven cleaner, 13.5. Bleach, 9.5. Egg whites are slightly alkaline at 8. Blood is slightly alkaline at 7.4. Distilled water is neutral. Blood is slightly basic. Milk is slightly, blood is slightly basic, but milk is slightly acidic. Coffee is acidic at pH of 5. Lemon juice is pH of 2. And of course, hydrochloric acid is 0. So you can see the different things that we encounter both internally and externally with our bodies and the various, acids and bases here. So why do we care? Our cells don't survive if our pH gets too high or too low. If we get above 7.45, our cells start breaking down. If we get below 7.35, our cells start breaking down. We don't like that. We don't like that to happen. Our cells are always releasing carbon dioxide. Carbon dioxide goes into solution in our blood on the way to the lungs and forms carbonic acid and makes us, if we didn't get rid of the CO2, we would continue to become more and more acidic. So we're sort of stuck at 7.4. Now consider what happens in cardiac arrest. A person's heart stops. Their heart is no longer beating. The muscle cells in the heart are still alive. They're just not functioning. The muscle cells in our bodies are still alive. It takes hours for all the individual muscle cells in our bodies to die. And as long as they're functioning, as long as they're alive, even though the brain may be dead, as long as those cells are alive, they're going to be releasing carbon dioxide. And that carbon dioxide makes us is going into blood. The heart's not pumping the blood. The CO2 is going into the plasma, making the plasma more acidic. Our pH starts dropping and cells start dying because we're getting too acidic. They can't function below 7.35. So a patient that has gone into cardiac arrest, for example, one of the standard treatments is to administer baking soda solution, sodium bicarbonate, to neutralize the carbonic acid that's forming. In the meantime, you're trying to get the heart started again, because you get about 5 minutes before the brain starts to die. Anyway, we pay very close attention to the acid and base concentrations in our bodies. Whenever an acid and a base come together, they will have a neutralization reaction. You will end up forming a salt and you'll form water. If you mix sodium hydroxide and hydrochloric acid together, you'll get sodium chloride and water. If you ever did the experiment in a science fair where you made a baking soda vinegar volcano, that was a neutralization reaction. You combine sodium bicarbonate, which was baking soda, with acetic acid, which was in the vinegar, and you ended up with the release of carbon dioxide. That was the bubbling and the fizzing. And you formed, water was formed and a salt was formed, usually sodium chloride. All this was taking place while you were, while the fizzing and the bubbling was going on. Whenever you have an acid and a base combined, you release water and create a salt. So now, acids and bases in our bodies depend on buffers. An acid, it only works if the hydrogen ions are free in solution. If the hydrogen ion is bound up to an anion, like for example, hydrogen and chlorine, hydrochloric acid, then the hydrogen ion is not free to roam and create this acidic environment. So if you can keep the hydrogen ion bound together, then your acid's not going to be very, very powerful. We use buffers in our bodies to hold on to these hydrogen ions. We can take a very powerful acid like hydrochloric acid and convert it to a very weak acid like carbonic acid, and we buffer, and we're going to buffer that strong acid into a weak acid that's not going to cause a problem for us. We want to tie up those hydrogen ions. Now we're going to hear a lot of it. We go into a lot of this when we get into fluid and electrolytes in AP2. Essentially, our bodies are always trying to keep us in that range. We use a buffering system to keep us in the range of 7.35 to 7.45. And if we can tie up the hydrogen ions, then we don't have to worry about the acidity. So, which now leads us into the more interesting aspects of the organic compounds, and that is the organic compounds, biochemistry. The organic compounds. This is much more interesting than the inorganics. The organic molecules all contain, at least that's my opinion. Organic molecules contain carbon. They are all neutral. They are all, so they're not basic. They are not acidic. They have no charge. They always share their electrons. So organic compounds share electrons. They don't give up electrons like ions do. They're not going to grab electrons. They will form covalent bonds with other elements. Typically, carbon will form 4 bonds. Carbon is the key to organic molecules. Carbon has 4 electrons in its outer shell. It wants 4 more, and it will create 4 covalent bonds to get those 4 electrons. Living systems use carbon. Organic material, plants and animals, humans, dogs, cats, trees, shrubs, everything uses carbon. Carbon has this unique ability, unlike any other molecule, to create bonds with 4 other elements. Now, the organic compounds we deal with in our bodies are the carbohydrates, which become the sugars and the glycogen, the lipids, which are the fats and cholesterol and steroids, the proteins, and the nucleic acids, the DNAs and the RNAs. Now, if you are an organic compound, you are probably a pretty large molecule. We call them polymers. We call that a polymer is a very long chain molecule. Lots and lots of carbons and hydrogens in here, made up of smaller structures. In the case of something as even simple glucose, a simple sugar, it's made up of 6 carbons and 12 hydrogens and 6 oxygens, one after another after another. Now, in sucrose, which is table sugar, you have 12 carbons linked together. And if we look at starch or glycogen, we have tens of thousands of glucose molecules linked together. So the polymers are made up of smaller units called monomers. So these polymers, long chain molecules. And we see that in the carbohydrates, we see it in the fats, and we see it in the proteins. In carbohydrates, we have a 1 to 2 to 1 ratio of carbons and hydrogens and oxygens. For every carbon we have in a carbohydrate, we're going to have 2 hydrogens and 1 oxygen. The simplest carbohydrate that our bodies deal with is glucose. It's what we call a simple sugar. It is, but however, as simple as it is, it's what our bodies use for fuel. We convert all the carbohydrates that we consume into glucose to release the energy, the potential energy stored in a molecule of glucose. So we use it for fuel, we use it for structure. Glucose is a 6-carbon sugar, 6 carbons in the sugar molecule. Another type of carbohydrate is ribose sugar. It has 5 carbons. Ribose sugar is what we use in DNA and RNA. DNA is called deoxyribose, and RNA is called ribose, ribonucleic acid, meaning it has 5 carbons. Now, if you're a sugar, you come in 3 categories. You are a monosaccharide, which is a simple sugar, and that's usually a 6-carbon sugar, but it can be a 5, and in some rare cases, it can be a 4-carbon sugar. The disaccharides are 2 sugars linked together. Sucrose, table sugar, stuff that comes in the white packets, the stuff that you dump into your coffee, that is a disaccharide because it contains 2 simple sugars together. And then we have the polysaccharides, the multiple sugars. This is a large polymer. This is a polymer is made up of lots with many monosaccharides. Glycogen, the substance we use to store glucose in our bodies, glycogen is made up of tens of thousands of glucose molecules in a long chain. Starches that we eat when we eat potatoes or carrots or beans or anything like that, any kind of plant material, eat an apple or banana, whatever. The starches are the same thing. The starches are glucose linked together. Starch and glycogen are equivalent. They're not the same. Starch is how plants store glucose. Glycogen is how we store glucose. This is a monosaccharide. It is a 6-carbon ring-shaped structure. It can be anywhere from 3 to 7 carbons, but generally, glucose is 6. There's a lot of energy stored in those covalent bonds. You have the covalent bonds with the 6 carbons, the 12 hydrogens, and the 6 oxygens. There's a lot of potential energy from all those covalent bonds. Now, the most important monosaccharides are going to be, of course, the ribose and deoxyribose for our DNA and RNA. And those are the 5 carbon sugars. But the most important ones that we pay attention to are the 6 carbons, glucose. We call it blood sugar or blood glucose. It's the sugar that's in our blood. There's also fructose. And if you want to know where we use fructose a lot, consider if you're drinking a Coke or a Pepsi right now, or a Mountain Dew. The sweetener in most of our soft drinks is high fructose corn syrup. And we don't use cane sugar anymore. We don't use sugar. The soft drink manufacturers all use high fructose corn syrup, unless they are doing the throwback version, for example, the retro, like retro Mountain Dew or retro Pepsi or something like that. I noticed that Coke never does a throwback. Maybe they're afraid that people will realize how good Coke used to taste before they switched to high fructose corn syrup. And then there's galactose, a third type of simple sugar. So these are the monosaccharides, glucose, fructose, and galactose. They all look very similar. They all have 6 carbons. Glucose is in a 6 carbon ring, but it has its oxygen located there to make the hexagonal ring. Fructose is a pentagonal ring. It has its other carbons sticking off and branching out here. And here's galactose, very similar in its structure. Its structure doesn't matter for what our concerns are. Glucose, fructose, and galactose. All 3 of them have a great deal of potential energy. They're all very similar, except in how they're very similar in structure, just where the carbons are located. The disaccharides are the double sugars. We can't get the disaccharides into a cell. Now we can get glucose in. Glucose can go across the membrane of a cell with help. But the disaccharides are too big. They can't get across the cell membrane. Even with help, they can't get across. The ones we deal with here are sucrose, that's table sugar. Maltose, which is malt sugar, we use that for baking, and particularly in commercial baking and in alcoholic beverage production. And lactose. Lactose is milk sugar. It's the sugar found in dairy products. So for example, to get sucrose, we would link glucose and fructose together. That would give us table sugar, sucrose. If we have, for example, there at the top is sucrose, which is glucose and fructose. If we link galactose and glucose, we get milk sugar. And if we link maltose, if we link 2 glucoses together, we get maltose. Now, the only difference here is that some of these sugars, in the configurations of some of these sugars, may cause digestive issues. Some people cannot process lactose. They're lactose intolerant. Some people can't process galactose. They are, this is unusual, but it happens. They are galactose intolerant, which means it doesn't enter the cells. It doesn't break down into glucose like it should. It doesn't release the energy. And so you have lots of complications here. Some annoying, some life-threatening here. So while there are very few differences in here, the structural differences can, in infrequent cases, and in some cases in rare cases, alter the ability to absorb these nutrients. Like, we've all heard of people that are lactose intolerant, that can't process dairy. And that's more of an annoying, or it's more of an unpleasant, annoying condition, which could be, I mean, any one of these could be life-threatening, but it's lactose intolerant can become truly life-threatening then. So, okay. Now the third category, so we've got monosaccharides, glucose, and fructose, and galactose. We've got the disaccharides, we have sucrose, and we have maltose, and we have lactose. Now we have the polysaccharides, which are long chains of glucose. Starch is a polysaccharide. Starch is what plants use to store glucose. When a plant's busy photosynthesizing, capturing energy from the sunlight, it's using that energy to combine carbon dioxide molecules with water and oxygen, with water, and release oxygen to give you glucose. And then they take that glucose and store it. Maybe they store it in the leaves, maybe they store it in the root, like a tuber, like a potato, for example. Well, humans don't store our excess starches, excess glucose, in the form of a starch. We eat a potato and we break that starch down to glucose. And if we have excess glucose, more than our cells can take in, we're going to store that glucose in our liver as glycogen. So the glycogen is how we store starch. So our, the starch starch in plants, glycogen in humans. So, and here are the the types of polysaccharides that we encounter. It doesn't take, a plant will convert some of its starch into cellulose. Cellulose fiber, the stuff we see in plants, the leafy greens we all like to eat, are not digestible. They are made of cellulose. Cellulose is what plant cells use to create their cell wall with. So our bodies can't process cellulose. Plants will store some of their sugars, convert them into cellulose. And so we can eat it, but we can't process it. It becomes what we call fiber. Food that's high in fiber has lots of cellulose present. Now, for example, if you like raisin bran, the bran is the outer covering, the husk, if you will, of the wheat kernel. Now we can eat the wheat kernel, but we can't eat the husk. We can't eat the bran. The bran goes through us as fiber. We like to have a high fiber diet. If you like to eat salads, like if you like spinach salad, for example, the cellulose in the spinach is not digestible. It creates a high fiber environment, so you sort of pass it through your bodies. It's why we can't go out and graze off of off leaves off of a bush or eat grass. We can't process it. We can't get any nutrients out of it. So cellulose, is the ultimate storage form of starch in plants. So it doesn't do us any good. Now, what about lipids? The fats, we say the triglycerides. Triglycerides, a term that we often hear a lot in talking about healthcare. Lipids also have carbons and hydrogens and oxygens. We don't have as many carbons and hydrogens and oxygens in the lipids. Sometimes we throw in phosphorus in here into the mix. Lipids are different than the carbohydrates. The carbohydrates will dissolve in water with a little help. Lipids don't dissolve in water. They're insoluble in water. Lipids also contain much more energy. A gram of carbohydrates contains 4 calories of energy. A gram of lipids, a gram of fat, has 10 calories of energy available to us. So, but we use glucose as our source of energy, not fats. Now, there are 4 different types of lipids. The triglycerides, one we pay a lot of attention to, particularly in healthcare. The triglycerides, or the neutral fats, meaning there's no charge on it. We also have the phospholipids. We'll talk about that, but that's what makes up the basis of our cell membranes. The steroids are what we use to make cholesterol, and cholesterol in and of itself is, has been classified as scientifically evil because of what excess cholesterol does to our body. But cholesterol in itself is not really evil. Cholesterol is what we use to make the steroid hormones, like the sex hormones, for example, and cortisol and aldosterone, all these important hormones that we need. And then we have the eicosanoids. This is like this is an anti-inflammatory lipid. Now, the triglycerides, they are fats when they're solid and oils when they're liquid. They're made up of 3 fatty acids linked together to a glycerol molecule. A fatty acid is just a very long chain of carbons and hydrogens linked together in covalent bonds, maybe 20 or 30 carbons and hydrogens linked together covalently with what we call an acid group, an acid chemical group at the end of the chain. That's what makes it an acid. So it's a fatty acid. A lipid, a triglyceride, consists of 3 fatty acid chains held together by a glycerol molecule. Glycerol is an alcohol molecule. It consists of 3 carbons and an alcohol group attached to it, just like an acid group attached to the fatty acid. Here we have an alcohol group attached to the glycerol. So we got a glycerol 3-carbon molecule with 3 fatty acid chains attached to it. Triglycerides are great for energy storing. We store lots of energy in our lipids. If your patient likes to consume lots of carbohydrates, more than the cells can use, more than can be stored as glycogen in the liver, those excess carbohydrates will end up being stored as as fat in the adipose tissue. And so that's how we end up with a person who consumes lots of fat in their diet or lots of carbohydrates in their diet we'll see more than they can process. We'll see more of those carbohydrates or excess fats becoming stored in their adipose tissue. They'll gain weight. We also use, we're storing it as energy. That's the thing. We're storing that excess energy in the form of lipids in the adipose tissue. The other thing we use lipids for is for insulation. In our hypodermis, we have a layer of adipose tissue filled up with lipids to keep us warm in cooler temperatures and cool in hotter temperatures. And so we insulate our bodies with a layer of fat in the hypodermis. We also use it for protection. Many of our organs in the viscera do not have any kind of protection from bone. And so they're cushioned in a big layer of fat. Like our kidneys, for example, are held in place high up in the back of the abdominal cavity, directly underneath the rib cage, cushioned in a big layer of fat. That's their only protection. So many places where we will have, where we have our viscera otherwise unprotected, we will build a layer of fat around them to protect them. This is what a triglyceride looks like. There's your glycerol molecule on the left-hand side with your 3 carbons and your alcohol group attached to it. There are your fatty acid chains, 1, 2, and 3. The alcohol group is on the left end of the fatty acid chain. So you don't worry about that. But all a fatty acid chain is carbons and hydrogens linked together. And now the three fatty acids, has to be three fatty acids here, are linked to the alcohol, the glycerol, to give you the complete triglyceride. And so we see it on the far right-hand side of the picture here. We have three fatty acid chains attached to the glycerol molecule. It carries a lot of energy and has some very unique properties here. It can be a solid or it can be a liquid fat. Now lipids, the lipids here, the triglycerides, we're talking triglycerides. Lipids are made up of, can be made up of saturated fatty acids. A triglyceride, the number one lipid here. A triglyceride can be made up of what we call saturated fatty acids. In a saturated fatty acid, we have every carbon in the chain held together with a single covalent bond. So we have the maximum number of hydrogen ions, hydrogen atoms here, not ions, but atoms. We're saturated. We have every possible place where you can have a hydrogen atom attached to a carbon. So you have a carbon at the end with three hydrogens. You have a carbon and two hydrogens, a carbon and two hydrogens, a carbon and two hydrogens, because of course the carbon is attached to, each carbon is attached to two other carbons. So you have all available places to have a covalent bond filled up with hydrogens. We are saturated. A saturated fatty acid is going to be solid at room temperature. It's an animal fat. Butter and lard are animal fats. They are naturally saturated fatty acids. They are solid at room temperature. If you ever looked at a label on an oil or the ingredients on any food item will tell you how many, the type of fats there are. They saturated or unsaturated? If it's a saturated fat, it'll have X number of calories. If it's not, and grams and calories. And if it's unsaturated, it will have grams and calories. It may even give you the various types of unsaturated fatty acids. But a saturated fatty acid will be solid at room temperature because it will have the maximum number of hydrogens it can possibly hold, bound covalently to throughout the polymer. So there at the top of the picture is a saturated fatty acid. It has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, and each carbon is attached to at least 2 hydrogens. And each carbon is attached to 2 other carbons, except for the one at the far end where you have 3 hydrogens attached. But every possible space where you can have a covalent bond, you're going to have a hydrogen. And that is a saturated fat. Now, the other type of fat, of triglyceride, is made of unsaturated fats. Now, there's a term you've probably heard of also. Unsaturated fats. Unsaturated fats are different. They don't have all their spaces filled up with hydrogens. What will happen is that in an unsaturated fat, somewhere you'll have in the chain, the polymer, you'll have a double bond between the hydrogens, between the carbons. And at that double bond, the chain, the long polymer chain of carbons and hydrogens will have a kink in it. It will have a bend in it. It will have a twist in it. And so you have the carbons and the hydrogens. And you'll have a bend in the chain. And unsaturated fatty acids are liquid at room temperature. The oils, olive oil, corn oil, vegetable oil, sunflower oil, safflower oil, canola oil, all of these are liquid at room temperature because they are made up, they have unsaturated fatty acids. Now, what's that mean? Well, your typical fatty acids can be anywhere up to 20 carbons in length. It will have lots of hydrogens and carbons bonding together. There may be, if there are no double bonds in the fatty acid chain, it is saturated and it is a straight line. If there is one double bond in there, there will be a kink in the shape of the chain, and it'll be, meaning it'll bend, and we will say it is an unsaturated fatty acid. If there's one double bond, it's an unsaturated fatty acid. If there's more than one double bond, it's polyunsaturated. Now, those are terms you've seen probably in advertising, or maybe if you ever bothered, you know, I mean, who takes the time to read labels on oils and fats and stuff like that? But an unsaturated fatty acid has one double bond, and a polyunsaturated fatty acid has at least two, but maybe more double bonds between the carbons. Here's what it looks like. Up in the upper right-hand corner of the screen, you see what's known as palmitic acid, which is a saturated fatty acid. It's a straight chain, but next to it is oleic acid, which is a fatty acid with a double bond, somewhere about the 4th or 5th carbon. That double bond allows it to bend and kink at that particular position. It's not a straight line anymore. Yeah. So a saturated fatty acid, it runs in a straight line. It's a solid at room temperature. It has all of its spaces available for hydrogens filled up. But an unsaturated fatty acid will bend. It doesn't have every covalent bond filled up with a hydrogen. It has at least one double bond between its carbons. Now, saturated fatty acids stay together thanks to van der Waals attraction. It is van der Waals attraction. Let me go back. Sorry. It is van der Waals attraction between if you have an unsaturated fatty acid chain, you have, if you have 3 saturated fatty acids side by side in straight lines, they are going to be attracted to each other by van der Waals attraction. Remember van der Waals attraction? As the electrons randomly move back and forth, occasionally they create a slight positive and negative charge, which is very transitory. It will form and go away and form and go away. But when it forms, it will be attracted to the saturated fatty acid chain next to it. And those chains will stick together. So all 3 chains stick together and essentially form a solid fat. Butter is a solid fat. Animal fat is a solid fat. Lard is a solid fat. All linked together through van der Waals attraction. Whereas the unsaturated fatty acids are liquid because the double bond that forms here prevents them from sticking together. The double bond allows the individual chain to kink, and it will also pivot around that double bond. And when it does that, it can't stick together. And so these plant fats are naturally going to be unsaturated. The corn oils, the canola oils, the olive oils, all of these are going to be liquid at room temperature. Now, fatty acids. Fatty acids, let's say that is all right. There we go. Okay. On the wrong direction. Hang on one second. Okay. Now, an unsaturated fatty acid is considered a fairly healthy food group. In an unsaturated fatty acid, you have double bonds holding the carbons together. You've lost a couple hydrogens here. So you've got these double bonds holding the carbon, so you're missing a few hydrogens. The lack of hydrogen atoms and their electrons is just enough to keep van der Waals attraction from occurring between the adjacent chains. So the chains don't have a chance to form a solid. These are all liquid at room temperature. Plant fats are liquid at room temperature. Olive oil, corn oil, canola oil, safflower oil, plain old vegetable oil are all going to be considered unsaturated, and they're going to be liquid at room temperature. Now, problems. Sometimes these plant fats can be converted into solid fats, and they form something that are called trans fats. So, for example, in beef cattle and in dairy cattle, they eat grains. They eat, hay. They eat corn. They eat whatever cows eat. And the oils in those plants are all unsaturated. But as they eat those fats, they convert them into solid fats. They form trans fats naturally, which increase the fat content of meat and dairy products. And trans fats tend to be a little less healthier for us than the unsaturated fats. So trans fats, in high quantities may be considered unhealthy. Let me explain what I'm talking about here. Let's watch this animation. See if I get the sound. Well, that was useless. Okay. Let's try it again.
Butter, lard, margarine, and salad oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules.
Okay, so that's a good little summary of what a fat is. Now, polyunsaturated fats. Why do our bodies like polyunsaturated fats more than saturated fats? Well, first of all, this is a polyunsaturated fat down here. We have 2 double bonds in the chain. We have a double bond here and a double bond here, so we have fewer hydrogens. It's unsaturated. Here we have a monounsaturated fat, 1 double bond. Regardless, it is, both of these are going to be liquid fats as opposed to solid fats. Up here we see a very small but simple saturated fatty acid here. It only has 3 carbons, but this is butyric acid. 3 carbons, but it's a saturated fat, no double bonds. You have a double bond in the chain and in a fatty acid chain, and now it's unsaturated. The problem that we run into with fats is, well, first of all, we like fats in our food. Fats make food taste better. It makes it easier to digest. It makes it gives it a creamier texture. It gives us more flavor in our foods. But the other problem, so we like fats. Now, chemically, unsaturated fats can be converted to saturated fats through a process known as hydrogenation. We can make, by breaking those double bonds and forcing the hydrogens back onto the fatty acid, we can take the plant fat, which is liquid, and convert it into a solid. That's how Crisco shortening is made. That's how any margarine is made. You take the liquid fat and you hydrogenate it and turn it into a solid fat. And the advantages are stability. The advantages are a whole new product. You know, Crisco shortening replaces lard. What do we use shortening for? We use shortening in baking. Shortening is what we use so that we can make biscuits that don't look and taste like a hockey puck, because shortening allows the dough inside a biscuit to separate into multiple layers, and we have very light and fluffy biscuits. It's how we make pie crusts to be light and flaky. You know, pastry shells have a lot of fat in there, usually in the form of lard. Most of your high-end bakers are going to use lard for their pastries because it creates a lighter product. Because what happens is as the fat breaks down, it releases carbon dioxide and a lot of water vapor. The water vapor in the form of steam causes the pastry shells the layers of the dough inside to separate into thinner and thinner flaky layers. Anyway, I'm not a baker, but that's what happens. If we don't want to use lard, animal fat, we use shortening, which is like Crisco or any of the other shortenings out there, which is nothing more than plant oils with the hydrogens put back in there. The problem with that, of course, is that the hydrogens, you create this white, you know what Crisco looks like, it's white. Well, that's what any hydrogenated plant oil looks like. You have to add salt and flavorings to it to give it any kind of flavor. Margarine, when margarine is made initially, it comes out white with no color to it, and you have to add a lot of chemicals to it so it has the correct, it tastes like butter. To get margarine to taste like butter, you have to add flavoring agents and coloring agents to it to give it that flavor. So you're trading off the trading off natural butter with its higher fat content versus the lower fat content in margarine, but all the chemicals added into it. So it's sort of a trade-off here. Another problem with hydrogenation is that you can end up creating what are known as these trans fats. Trans fats form solid fats at lower temperatures than what we call the cis fats. Cis and trans refer to the position of a molecule of the components of a large molecule, whether they are on the left-hand side or the right-hand side of a molecule. That's all cis and trans mean. And so we see the cis and trans fats here. Which way does the molecule turn? And so by hydrogenating a fatty acid, you may have more hydrogens on one side than on the other side. And that creates a cis and trans approach. What do we use trans fats for? Trans fats increase the shelf life. It improves the texture. You know, when we hydrogenate foods, it has a creamier texture. It holds the flavor better. Peanut butters, for example. Peanut butter was, when it was first manufactured, would have the oil at the bottom and the oil on the top and the peanut paste in the bottom, and you'd have to stir it up. It was long before any of our times. We're used to peanut butter. You open a jar of Jif or Peter Pan or something, and it's nice and creamy, and it's good. Well, 100 years ago, peanut butter had to be stirred up because the oil was on the top and the peanut paste is on the bottom. And then someone got the brilliant idea of hydrogenating the oil, and suddenly you have this creamy peanut butter mixture that lasts on the shelf a long time. The oil doesn't go rancid, and the flavor stays, consistent. Downside of the potential production of trans fats. Here we see margarine. Margarine is an unsaturated fat. It is hydrogenated. You take the unsaturated fat and hydrogenate it by adding hydrogens on there, break the double bonds, and then you get, all these examples of artificial butter. And this ad on the right I think is from World War II, where the dairy industry forced the margarine manufacturers to have a flavor and coloring packet inside a pouch of margarine. And you'd have to break the pellets and then mix it all together. So you would have your artificial flavored margarine and artificial colored margarine. So, because it all came as a white block. So, okay, let me just say one. Let me just stop here at trans fats, and we'll pick up with this again on Wednesday. Hopefully, everybody will be back in the building, and we'll have air conditioning too. Okay, let's all this. I'll get this posted for you.